This lesson is on exponential modeling, otherwise known as word problems. This first page, we just have the 4 types of word problems we will be doing: depreciation or decay, appreciation or growth, compounded interest, and compounded continuously. So make sure that you have your highlighter. You must memorize these 4. So make your flashcards now. The important part is I gave you an example for each, so I would like you to pause the video when I'm done explaining what the variables mean for you to read through all the examples. So the first one is decay, and you'll notice growth and decay have the same equations except for one's a plus and one's a minus. One's adding the rate and one's subtracting the rate. The reason that there's the 1 is because the rate is in a percent, and if I add 1 plus 5%, it's 1.05. That's really 105%. So I'm adding the 100% I had and then 5% more. So that's where the 1 comes from. So in this first one for decay, y is my end value, or my now. A is my start value, or my initial value. R is my rate as a percent, and the good news is you have a percent button on your calculator, so you don't have to convert anything to a decimal, unless of course you want to. And then T is your time. Now the big thing you have to remember is that your rate and your time have to be the same label, meaning your rate can't be compounded in months and your time is given to you in years, or vice versa. So they both have to have the same label. Either they're both annually or yearly, or they're both monthly. And if they're not, then you have to use a different formula, or you have to do something prior to that. So the good news is that these things are exactly the same for growth. So make sure to pause the video and write those down again. Now, compounded and compounded continuously give students some headaches. You only use compounded when it has that word compounded, and then it's going to say one of these words: compounded daily, compounded monthly, compounded quarterly, compounded semi-annually, compounded annually. And in reality, annually is just your growth. So annually means one time. Well, if I put a 1 in for this end value, dividing by 1 and raising it to the 1 power is exactly the growth formula. So keep that in mind. Usually they don't try to trick you that way. They don't say compounded annually. They just say, I don't know, some way that it's 20%, like in the example about 20% every year. I don't know. So if you have any questions on that piece, let's talk about that a little bit more in class. But if not, I mean, you can use this formula for annually. You're just putting 1s in, and sometimes that's okay. It just looks weird. So daily, we're going to assume 365 days. Monthly is 12. Quarterly is 4 times. Semi-annually is 2. So here's the catch. You got to know those. So you have to know that when it says compounded monthly, that end value is 12. Okay? So please make sure you know those. Now the Y, the A, the R, and the T are the exact same from growth and decay. And I try to keep them the same. If you Googled this, you would see these exact same equations written with different variables. So don't get hung up on the variables, get hung up on what the variable means. Where is its placement in that equation? So again, Y is your end value, your now. A is your start value, or your initial. R is your rate, as a percent. N is the number of times compounded. And T is your time. Okay? So this is the equation when those labels are not the same. When they say the rate is compounded monthly and your interest is in years, this is the equation you use when they don't match. Okay? And the last one is the one that most kids kind of dismiss and forget about, continuously. Okay? There's no number for continuously. That's why we use a different base. We don't use 1 plus or 1 minus. We use the E value. Okay? So again, Y, A, R, and T are exactly the same as above. You have your end value, your start value, your rate as a percent, and your time. All right, so go ahead, pause the video now and read through the examples. Make sure you're good to go. Write down any questions you have. All right, let's practice. So we have our 4 equations at the top, and exponential functions are very important in modeling a variety of real-world phenomena because certain things either increase or decrease by fixed percentages over given units of time. So they increase or decrease by a fixed percentage over time. So in exercise 1, you're depositing money into a savings account and you receive 5% interest per year on the amount of money that is in the account for that year. Assume you deposit $400 into the account initially. That's a key word. How much will the savings account increase over the course of the year? So the first year we have $400, so we're growing, so we're going to use our growth formula. So we want to find out Y equals, our start value is 400, 1 plus, we have 5%, and what's our amount of time? Well, 1 year. So we're going to grab our calculators. We have 400, 1 plus 5, and the percent button is next to the letter G, raised to, raised to, and I don't really have to do this, I could just have hit enter. We made $20, so it equals 420. But the question says, how much will the savings account increase? So our answer to this question is $20. Okay? How much money is in the account at the end of the first year? Well, that's this answer. So $420. So what I could have done if I was just doing 1 year is just multiplied 400 times 5%. That'll give me the amount of increase, and then just add it to my initial amount. But using the formula allows me to find its compounded interest. So over time, how much would I have made in the 5th year, the 8th year, the 20th year, whatever. So by what single number could you have multiplied the 400 by in order to calculate the answer from part B? And that's our 1 plus the rate. So 1 plus 5%, which hopefully you know is 1.05. So give an equation for the amount in the savings account as a function of the number of years since 400 was invested. So they're telling us to use S of T, which equals 400, 1 plus 5% raised to the T. Because remember, function notation, this variable has to match this variable. And S stands for our savings account. So now it says, using a table on your calculator, determine to the nearest year how long it will take for the initial investment of 400 to double. So let's grab that calculator and we're going to graph it. So I'm going home and adding a graph. I'm putting in 400, 1 plus 5%, and I can't put T in this time because this is f of x So I have to now convert that to x, or I needed to change that x in the function notation, and I see nothing. Well, $400, that's my y value. X is my time. So maybe I just need to change this. I'm going to try 1,000. Hit tab. Oh, now I can see it. I'm going to do, I don't know, 50. Hit tab. I don't need anything at the bottom, so I'm going to hit 0, and then I'm going to hit 0. All right. I need to know where it's going to double. So it says to use our table. So Control T. We want to know, well, look at the table. Times 0, or initial amount, we had 400. So times 0 is our initial amount. First year, we had 420. Second year, we had 441. We're assuming that we're not adding any money in. So we want to look for where we hit 800. Ah, there we go. Between the 14th and the 15th year. So write down your table with the 14th and the 15th year in it. And your answer is what? So you have to be careful because it says to the nearest year, how long will it take for the initial value to double? Well, yes, 14 is closer, but you have to say 15 because at year 14 have you doubled. So you're going to write your sentence using that idea. So by year 15, the initial value would have doubled. If we're going to say during is when it's happening in that year, okay? But by the 15th year, we could have also said during the 14th year, the initial value has doubled, okay? Because remember, these assume this is the beginning of that year. So this is like January, all right? All right, decreasing exponentials are developed in a way, but have the percent subtracted rather than added to the base of 100%. Just remember, you are ultimately multiplying by the percent of the original that you will have after the time period elapses. So in exercise 2, they're asking you to state the multiplier or the base that you would need to multiply by in order to decrease a quantity. Okay, that is important. Decrease the quantity. So we're looking at decay. So we're looking at the last equation on the top of the page. So they want the multiplier, the base. So that's the thing in parentheses. So that's the 1 minus r. So if I do 1 minus 10%, if you have to pause and use your calculator, then do it. It is 0.9. 1 minus 2% is 0.98. 25%, 1 minus 25% is 0.75. And 0.5% is 1 minus 0.5% is 0.995. Now, you guys, this is something you want to definitely star. These are the questions you get wrong. So we are going to give you equations and ask you to explain what the numbers mean. And decay questions are always the ones kids get wrong. And it's because they see, oh, 0.9, that's the decay factor. No, okay? 10% is the decay factor, or the decay amount. You're decreasing this by 10%. 0.98 is 2%. 0.75 is 25%. So with decay, the number that you see is the 1 minus the rate. That is very difficult for kids. So take a minute, pause the video, or before you start part 2, and think about that. Think about how that impacts your work. All right, part 2 is next.